Hi guys, welcome back to the Making Links series for season 10. We're now on how do we measure rate of reaction. And there's a couple of ways that we can do that, but first of all we need to understand what exactly is rate and what are we talking about. Basically, we can measure how fast the reactants are used up, or we can measure how fast the products are made. Have a look here. This would be the 0 seconds. This would be the start of the reaction. You've got a ton of reactants and no products. So if the reactants are red, the products are blue. So we've got here 1 mole of A. We've got no products at all. This would be A makes B. At 20 seconds, some of your reactants have turned into products, but not all. And then at 40 seconds, you've got more products than you have reactants. So we can measure one of two things. We can measure how fast the red is reducing over time, or we could measure how fast the blue is being produced over time. Both are valid ways. It would depend on how easy it was to measure both. So the actual textbook definition is the rate of a chemical reaction is equal to the change in concentration of or products per unit of time. And that unit of time can be anything, which we'll have a look at in a minute. So you write it as two equations. It's either the increase in concentration of product over time, or it's the decrease in reactant concentration over time. Unit of time can be many different things. It could be something really fast. It could be in milliseconds. In this case, we couldn't realistically, we couldn't measure how fast the reactants were used up over time, but we could measure how fast the products were being made over time because we can see the products. But the unit of time would be milliseconds. Here, we'd be looking at seconds. So here we're looking at the precipitation reaction, which we'll look at in a lot more detail when we do paper 6. But the unit of time would be seconds, and we could measure how fast our product was being produced over time because we can see it. It's easy to measure. When we do something like the sodium thiosulfate experiment, we're doing a very similar precipitation reaction. This would be something like digestion. Good old Mr. Trump there, eating his, I don't know what that is, but it doesn't look very healthy. Digestion happens over hours. Again, we could measure how fast something was being used up. We could measure the decrease of something over time, but we could also measure how fast something like poo was being made, I guess, over hours. And this would be over years. We would measure how much rust would appear over years, or how much product was being made over years. So how do we measure it? You need to know of 3 ways, and they all involve measuring products produced over time, which is the most common way to measure in the lab. All of these involve the production of a gas, and they might ask you about any one of them. In this case, we've got a metal plus an acid, so we're making hydrogen. We have an electric balance. When we produce the hydrogen, which is our product, it is going to rise up here and escape out past the cotton wool and out into the surroundings. That's going to measure as a decrease in mass on the balance. You can measure how fast the mass decreases and plot that on a graph. You can take the mass at regular intervals over time, and you can plot that on a graph. You will get a curve to show the rate of reaction. The reason why we've got cotton wool in the top is to stop splashing. So if there was bubbling and fizzing and some of the hydrochloric acid was jumping up here, you wouldn't get liquid leave the container, so that wouldn't affect your mass. You wouldn't lose liquid, you would only lose gas. It's a good way to measure rate of reaction if you've got a gas being produced, but it's perhaps not the most reliable and most precise way of measuring. This is another way, not very good if your gas is soluble in water. So you can't use it if you've got a soluble gas. However, exactly the same reaction. We've got, say, hydrochloric acid, magnesium ribbon. You've got a bung here to seal the tube, a delivery tube that comes down. We usually put something like a beehive shelf underneath. The gas just comes out here and is bubbled up through the water. At the start of the experiment, you need to make sure that the water is fully up to the top. You can't have any space whatsoever left over. And then what will happen as the gas is produced, it will displace the water. The water will end up coming out and the water level rising here, and you will end up with all of your gas trapped here. You will then be able to read off on your measuring cylinder how much gas has been produced. Again, not the most precise way of measuring, but it's pretty effective. This one's a little bit tricky to do as well, a bit messy, a bit tricky. If you want the most precise way of measuring, you would have a gas syringe. This would be a glass gas syringe. You would have your delivery tube coming in. All of your gas would come up here and it would be collected in the gas syringe. You need to make sure that your plunger is fully in at the start of the reaction. And as the gas is produced, it will push this plunger out and you'll just simply be able to read off where the plunger is at the end. This, if they ask you in an experiment, say they showed you this one or this one, and they like to ask the question, particularly in paper 5, how could you make this experiment more precise? You would draw out this equipment for a gas syringe. So once we've actually got some data, once we've measured over time, we can draw a graph. The graph will look something like this. In this case, we are measuring the amount of products produced over time because at T is 0, we've got no products. If we were measuring the amount of reactants used up over time, like the graph I showed you earlier in the earlier video, you would start up here and your curve would come down. Normally what we find is that we have a steep gradient at the start, or the line goes up pretty quickly. That means a fast rate of reaction, because the steeper the line, the faster the rate of reaction. Over here, you can see that the rate of reaction is starting to slow down. We know this because the gradient is getting less steep. What will happen is eventually you will level off. And when you get a flat line, that means that your concentration is not changing. It means you've either reached equilibrium if it is a reversible reaction, or it just means your reaction has come to an end. Don't forget, when we are looking at rates of reaction, not every reaction is reversible. So don't always state here, reaction has reached equilibrium, because it might not be the case. It might be just that reaction is finished. It is much better to say there is no further reaction, or the gradient is 0, or the rate of reaction is 0. So let's have a look. This is the kind of exam question you might get. How do the rates at times T1, T2, and T3 differ? So time 1, time 2, time 3, it doesn't matter. They might put numbers on these, they might not. Don't be alarmed if they just say T1, T2, T3. This is exactly this question here. So pause the video now and think about how you are going to get 2 marks for this exam question. Okay, so hopefully you've got your own answer. This is measuring volume of oxygen produced over time because it starts at 0. The first thing you have to do is compare T1 to T2. You can say the rate slows down between T1 and T2. The rate is slowing down. You know that because the gradient is getting less steep. But it's not an explain question. It's only 2 marks. You don't have to say because. It doesn't say explain how the rates. It just says how do the rates differ. It's a describe question. You can say the rate is 0 at T3 because we know this because the line is flat. But again, you don't have to write that in your exam answer because it doesn't say the word explain here. Next episode, we're going to look at how we increase rate of reaction. And there are 4 ways to do that. We're going to look at them in detail and do some more exam questions. See you next time.